Good morning, everyone. In this lecture, I'm going to talk about the luminosity and the apparent brightness. The luminosity is the total amount of energy that a star radiates. It's not only the star, it can be a light bulb or it can be any source of energy. And what is the apparent brightness? How much light it falls onto the earth, or how much light it reaches to the earth's surface. If you are in a room and when you turn the light on, if you go further and further from the light bulb, the amount of light reaching you is very small. That means the brightness, the apparent brightness, depends upon your position, how far you are from the source. The luminosity is constant. It is just the total amount of energy it radiates. The exactly same thing happens to the sun or to any star. So if you look, the sun, it radiates the energy in all possible direction, and the amount of energy that radiates, we call that as a luminosity. The luminosity is simply the energy released by the sun in 1 second, and the unit of luminosity is watt. And how much light reaches to the earth is called the apparent brightness. So the unit of apparent brightness is the watt per square meter, or energy per second per square meter. This is the apparent brightness. So as I mentioned before, the brightness of a star depends on both distance and luminosity. If you are far from a light source, then your luminosity, your apparent brightness, or simply called the brightness, would be very smaller. If you go closer and closer to the light source, to a light bulb, you see that the brightness is more and more, increases up. But if you move further and further from the light bulb, the brightness decreases, and it follows a inverse square law. The luminosity is a constant, and if you decrease the current in the light bulb, the luminosity starts decreasing. So the total brightness, or if you make the light bulb dim, you'll see the if you decrease the if you make the light bulb dim, the brightness decreases. So the brightness depends upon how far you are and what is the luminosity of the object. So let me ask you a question. The Alpha Centauri and the Sun have about the same luminosity. That means it releases the same amount of energy per second. For those who do not know what the Alpha Centauri is, the Alpha Centauri is the closest star system to our solar system, which is about 4.37 light years from the Sun. So it is just the Alpha Centauri is just the closest star system. So it does have three stars. We call Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. So it is a combination of three stars. And the two star Alpha Centauri A and Alpha Centauri B forms a binary pair, a binary system. So The question here is Alpha Centauri. If you look from the Earth, the Alpha Centauri and the Sun, which one does appear brighter? I mean, of course, you know that the answer. If you look in the sky and if you compare with the Sun, which one does appear more brighter? Of course, the answer is the Sun. You see, the Sun is much brighter. Why does it look so? Although the Alpha Centauri is comparatively releases more energy, but the Sun appears much more brighter. And the reason is the Sun is much closer to us than the Alpha Centauri. This table here, if you see the Alpha Centauri is 4.3 light years, but the Sun is only 93 million miles. So the Alpha Centauri is much further from us than the Sun. The Sun is much closer to us. That's why although the Alpha Centauri and the Sun have the equal luminosity, the Sun appears to us much brighter than the Alpha Centauri. Now we'll talk about the inverse square law. So let's say here you have the Sun and you come up with imaginary the sphere. The total amount of light passing through each sphere is exactly the same. Whatever passes through this sphere must pass through this sphere too. Whatever passed through this sphere must pass through this sphere. So the total amount of light that passes through each sphere is exactly the same. The only difference is the area, the surface area. The surface area of this sphere is much smaller than the surface area of this one. And you know that the surface area is directly proportional to r square. What is the surface area of a sphere? It is 4 pi r square. So now let's take a unit area onto the first sphere, which is as a distance of 1 astronomical unit. Remember, 1 astronomical unit is the distance, the average distance between the Earth and the Sun. If you take the 1 unit squared area, the light that passes through here, it also passes through the second sphere, but over a larger area. That means if I take the same unit area here, the total amount of light over the same area is about 4 times smaller than this area, because the radius here is 2 astronomical unit. So whatever light passed through one area here, it passes through the it passed through the 4 area. And if I triple the radius, 3 astronomical unit, then whatever the light passes through 1 unit area here, the same amount of light passes through the 9 of the area here. And if you recall, the brightness is the total amount of light that reaches to the unit area, which means if you go further and further, the brightness starts decreasing, and it follows the inverse square law. That means if you double the radius, the brightness goes down by 4 times. If you triple the radius, the brightness goes down by 9 times. If the radius increases by 5 times, the brightness goes down by 25 times. Okay, just keep this in mind. Now here I will give an idea, the mathematical formula for calculating the brightness. Remember, the luminosity is a constant. It doesn't fluctuate in a day, 2 day, or in a year, 2 years. It takes million years to change the luminosity. So for now, we just keep the luminosity constant. So what you see here, the brightness is luminosity divided by 4 pi distance squared. If the distance increases by 2 times, the brightness goes down by 4 times. If the distance increases by 3 times, the brightness goes down by 9 times, because these two are inversely proportional. This is exactly called the inverse square law. Okay. If you know the brightness formula, from here you can also calculate the luminosity. That's how we calculate the luminosity of the sun. We know what is the distance between the earth and the sun, and we measure the brightness on the earth's surface. So if you know this brightness, and using this formula we have calculated the luminosity of the sun. Now let me ask you some question, and this would be it's a very easy question, and this would be very helpful for doing your homework. How would the apparent brightness of Alpha Centauri change if it were 3 times further away? What is asking is, if the distance is 3 times more than what is today, or if we measure the distance 3 times further away, what would be the brightness? And you just remember now, from your intuition, from your experience, the further away you are, the lesser bright the object or the source looks like. So if you make it 3 times, just square this number, it's 9 times smaller, or what we call it will be only about 1/9 as bright. So if the distance increases by 3 times, the brightness decreases by 9 times, or what we call it will be the only 1/9 as bright. So this is all I have today for you on the topics of luminosity and the brightness, and I would like you to go through the chapter which talks about the luminosity and the brightness, and I also have mentioned what chapters you need to study to get a more deeper understanding of luminosity and brightness. All these slides will be very helpful for you to do your homework. If you have any question, let me know. Thank you so much. Bye bye.